All right, for this lecture, we're going to talk about probably one of the most widely used types of time series modeling, that is ARIMA modeling. So ARIMA modeling stands for, it's an acronym, it stands for autoregressive, it's the AR, integrated, it's the I, moving average. All right, so autoregressive, integrated, moving average. I know, kind of sounds like a lot of gibberish right now. However, as we begin to kind of work our way through the lecture, hopefully this abbreviation will start to make more sense. It's also less commonly referred to as a Box and Jenkins model, and I guess note in particular that I have this title slide labeled as a non-seasonal Box and Jenkins model. So right in this kind of introductory lecture, we're going to sort of not worry about this idea of seasonality that we've talked about previously, but of course we will eventually learn how to add seasonality into our model. So let's go ahead and get started.
So when you have an ARIMA model, there's sort of three different models that we might consider. One's called an autoregressive model, an AR model. One's a moving average model, an MA model. So right there's kind of, we're getting a sense of where this term ARIMA comes from, right? ARMA. I guess that's an ARMA model. And sometimes you do hear it referred to as an ARMA model. So we might say, well, what's this I? Where does the I come from in remodeling? We'll talk about that. We'll talk about that down the road. And then you can actually have a mix. So you can have a model or a real life situation, a real life phenomenon that is best modeled by a mixture of these two, right? A mixture of an autoregressive and a moving average model. And so we call that a mixed model. So an autoregressive model of order P looks like this, right? And I think of the two, autoregressive, moving average, probably the autoregressive is like the more intuitive one, right? So we have this autoregressive model of order P. And so it's basically saying that like the observation today, right? Say the stock price today, if it's of order P, right? I always think of like ARP. Isn't that like the I don't know, some kind of professional organization of retired people or something along those lines? So yeah, so ARP, autoregressive order P. So the observation today depends on the observation yesterday and the day before that and the day before that, and we keep going to P time periods back, right? And of course that P could be any whole number or integer. So we model the stock price today as a function of the stock price yesterday, day before yesterday, and so on. And of course, right, it's not going to be perfectly deterministic, so we add this error term. Now, right, we've essentially sort of taken the dependency out of our error terms by putting them in our model. And so the leftover error terms should ideally be independent. Now, again, we don't have enough time to really get into it, but one way you can test whether your model is sort of taking all of the dependency into account is to actually test to see whether those A's really are independent. But if you've modeled it correctly, they should be. If they're not independent, that's indicative of you modeling this thing incorrectly. So, I mean, this would be an autoregressive model of order one, right? Pretty straightforward. Actually, it looks a lot like what? It looks a lot like our autocorrelation, right? Our first order autocorrelation. And that in that case, we were looking at errors, right? The error today is a function of the error yesterday. Here we're looking at the actual observation y's as being functions of previous observation y's. Right, and this would be an example of order two. Right, so this is P equals 2. All right, nothing too profound there, just trying to write it out a little bit more explicitly. So yeah, so that covers an autoregressive model. A moving average model of order Q looks like this. So Here we modeled the stock price at time t, not as a function of the observations, right? The stock prices yesterday, but the error terms of previous time periods. And this one feels like a little less intuitive. I think it is a little less intuitive. Um, and it might also feel like very similar, right? Like, okay, well, isn't modeling it as like the errors of the time period yesterday kind of the same as modeling it based off like the actual observation from yesterday? And the answer is kind of yes and no. I mean, it's certainly right. It's obviously not exactly the same. Um, Now, is it sort of related? And the answer is yes. In fact, you can show that you could re-express a moving average model as an autoregressive model. You could re-express an autoregressive model as a moving average model. So sure, right? They are interrelated, absolutely. And again, if we had more depth, we can kind of explore this interrelatedness. But in practice, they're typically conceptualized as two distinct models. Now, right, whether we use pluses or minuses is a little bit arbitrary. I mean, most linear equations, the convention is to use pluses. Again, there is a rationale for kind of why we're using minuses instead of pluses in this case. But again, sadly, we don't have quite the time to get into it. So we'll just kind of take it in faith that the standard convention is to write these things as the coefficients in this term as minuses instead of pluses. Here's like a nice little so Chatfield's kind of like a big name in the time series industry, the time series field. He writes a lot of books. I think actually R is maybe his kind of preferred programming language when it comes to time series. But he writes, right, moving average processes have been used in many areas, particularly econometrics. For example, economic indicators are affected by a variety of random events, right? So here we're looking at not as a function of previous indicators, but as a function of previous random events, right? These A's, not the Y's, such as strikes, government decisions, shortages of key materials, and so on. Such events will not only have an immediate effect, but may also affect economic indicators to a lesser extent in potentially several subsequent periods, right? So up to, I didn't emphasize this, but we use Q as the order of a moving average model, right? MAQ, so Q subsequent periods. Right, so again, I'll do an order 1, and right next slide will be an order 2. So just to kind of show you what it looks like this is Q equals 1, and this is Q equals 2. Right, easy enough. So when you're working with an ARIMA model, probably the single most important idea is this idea of something called stationarity. All of the methodologies for these models assumes that the y sub t are stationary. And really how well your model works is heavily dictated by whether or not you have this stationarity. Now, for a set of y's, for a set of observations to be stationary, they must have a common mean and a common variance. There's a little bit more to it, but that's the big picture idea. That is, right, the plot of the data should look centered, right? That's the idea of the common mean, with the same variability along a horizontal line. Now, the reality is, right, very few time series look like a flat line with common variance. It's extremely rare that some kind of real life phenomenon is going to look like that. Which means what? It means that almost always we have to take something that is not stationary and make it stationary. And there's sort of two pieces to that, right? One is, how do I fix a non-constant mean? So non-constant means you have something that's like increasing, decreasing, right? Probably more realistically increasing at parts of your time series, decreasing at parts of your time series, but not flat. So how would I fix something like that? And the second thing we'll have to talk about is, well, what if the variance isn't constant? How do I fix that? But let's start with this idea of a non-constant mean which means that you have some sort of trend, right? It's going up, it's going down, maybe a combination of the two. How do I fix it? The most common way of fixing trend is to take what's called the difference of the time series. That is, rather than working with y sub t, we work with some transformed variable, let's call it z, where z is defined as the difference of y sub t minus y sub t minus 1. So z sub t is basically, right, how much at every time point, how much did the time series increase or decrease by? Right? We're no longer focusing on what's the stock price, but instead we're saying by how much did it go up or down? Often taking one difference will be just fine, but there are certain situations where it's not, and in that situation we might try doing a difference yet again, right, a second time. And as you can keep doing this difference operator. Now it might seem like a little bit magical, like why does taking a difference of observations fix trend? You can actually see it relatively easily. So imagine that we have like a linear trend, right? That we have something, the y sub t is just this linear function of time. So non-constant mean, right? Like if that beta 1's positive, then right, for large values of t, we expect y sub t to be larger. But what would it look like if I did y sub t minus y sub t minus 1? Well, I just plugged in that equation to both y sub t and y sub t minus 1. So what happens? Well, the beta knots cancel, agreed? And I probably, that's a mistake on my part, I probably should have put parentheses around the t minus 1, agreed? So I have beta 1 times t minus 1. I can distribute that beta 1 through, right? And that'll give me beta 1t minus beta 1. And then, right, I go back, I distribute a minus. So, right, look it through, but hopefully we could see that that plus beta 1t will cancel with a minus beta 1t. And all we'll be left with is just a beta 1. Pretty cool, right? So I can see very clearly how differencing, it's almost like taking a derivative a little bit, isn't it? Differencing, like basically, it ends up being like the derivative of that thing with respect to t is exactly what it ends up being, right? It ends up being just that beta 1. And then I'll leave it to you if you want to play around with it. If you want to actually draw what a quadratic equation, so add a beta 2 t squared, and you'll see that if you do one difference, it'll reduce that quadratic to a linear function. And then if you do a second difference, it'll then reduce that linear down to just this kind of flat coefficient, this flat line. So again, kind of like derivatives, right? That is, I have to take two derivatives of a quadratic to kind of get rid of the t. Yeah, pretty cool function, I think. Now, what about variability? Well, we're actually used to fixing violations of variability. Harkens back to our 512 days. In our 512 days, we just usually fixed right, violations of homoscedasticity by taking a log transformation, maybe a square root transformation, and that'll actually work just like before. So those are kind of the usual solutions to that problem. Okay, so given a data set or time series, there's now a number of things we would like to be able to test for. One is it's stationary. Two, is a moving average model appropriate? If so, what order, right? So first question is moving average appropriate? If it is, right, what's the appropriate Q? Second question is an autoregressive model appropriate? Right? If so, what's the appropriate order? What's the P? And then I guess we also have that thing, right, is a mixed model appropriate, but we'll talk more about that in a little bit. Now, different people approach the stationarity thing in different ways. Statisticians really seem to or tend to prefer just looking at the scatter plot of the y's. You look at the scatter plot of the y's and you say, okay, does the scatter plot look like it's a flat line with a constant variance? Econometricians, right, tend to like p-values, tend to like statistical test. Econometricians will use something that you may or may not have heard of called like a unit root test. There's lots of different versions of the unit root test to kind of test for stationarity. Statisticians prefer to just kind of look at the scatter plot. Now, to answer the question about a moving average model or an autoregressive model, well, we need a particular tool. And the main tool that we need is referred to as the sample autocorrelation function, often referred to as the SAC, right? Sample AC autocorrelation, and also abbreviated R sub K. So R is our usual function of correlation. We'll see that K is the correlation of time points separated by K time points, or the correlation of observations separated by K time points. Yeah, I guess I have it in that second bullet point. The correlation between observations, yeah, separated by K time units. So here's an example of an autocorrelation plot. It's on the left. So what is this thing? So first off, that bar. So first off, all of these are positive, but autocorrelations can be negative. So I mean, there's plenty of examples, right, where you have kind of some bars on the right-hand side. That is, some of these things are positive. Some bars are on the left-hand side. Some of them are negative. That's no big deal. It happens quite a bit. The way SAS puts this together, this is actually from SAS. The way SAS puts this together, that bar for 0 is essentially the correlation of observation with itself, right? Observation separated by 0 time points is just itself. So that's actually perfectly correlated. That has a correlation of 1. That's always the case. So that first bar is like, I guess, more of a reference bar than anything, right? It kind of shows us what a bar of height 1 looks like. And then it gets interesting from 1, 2. So when I'm going down when I'm looking along the left-hand side and it's going 0, 1, 2, 3, 4, 5, right? That's basically the K. That's like, right, the correlation of observations separated by that many time points. So when I look at that 1 and I look at its bar, it's a little less than 1, right? One of the cool things about this particular viewer, if I mouse over that bar, it'll tell me exactly what the number is for that. It didn't preserve with the screen paste, sadly. But if you do mouse over, it will tell you that correlation. I mean, it looks really close to 1, doesn't it? It looks like whatever, like 0.98. So what that's basically saying is the correlation between observations separated by 1 time point is 0.98. And then, right, we're seeing that the correlation between observations separated by 2 time points is a little less than that, maybe 0.95, right? And then like 0.93 and 0.90 and 0.85, right? It gets kind of slowly smaller and smaller. Now that little red line is essentially significance, right? So we can see that all of these things are significantly different than 0 until we get to like number 8 or so. Yeah. So again, this literally is an actual correlation, like from Proc Core in 512. In fact, right, in a time series class, I have people do some labs where they kind of prove this themselves. And right, if you have maybe some free time on your hand, I don't know, maybe you're quarantined for the next 3 months of your lives. I mean, you certainly could play around with it. Again, playing around with things, tinkering with things, again, is really the best way to kind of get a sense and internalize how and why things work. But if we say that correlation at lag 1 is, say, like 0.98, that's basically saying that if say you paired an observation, say you pair the observation at time point 1 with time point 2, and you paired the observation of time point 2 with time point 3, then you paired the observation of time point 3 with time point 4, right? Now we have these pairs of observations separated by one time point. And you ran proc core on it, you would get exactly that 0.98 or whatever that number is. If you do want to play around with it, the function that does that in SAS that you could use in a data step to help create these pairs is called the lag function, if you want to kind of Google it and play around with it. But anyways, that's the autocorrelation function. I think in a slide or two I talk about this idea that we would expect a diminishing correlation, right? That observations are related less and less and less the further back in time we go. We actually talked about this idea, I think, when we were talking about like positive autocorrelation. So this has like a perfectly diminishing pattern, right? So in that sense, it's very intuitive. I will say that this is in general a bad looking autocorrelation plot. So I said that typically we would assess stationarity by looking at the scatter plot, but a secondary way of assessing it is to look at this autocorrelation plot. And we typically want this autocorrelation plot to die down very quickly. That is, to get to 0 or something that's not significantly different than 0, like very quickly by like lag 2, 3, somewhere in that range. The fact that this thing takes up to like lag 8 is basically saying that the time series that I'm looking at is not stationary. Yeah. So if all the observations were independent, then we would expect that sample autocorrelation function to look like what? Yeah, exactly. We'd expect, and that's a typo, I guess. It shouldn't say autocorrelation function of the residuals. That's an autocorrelation function of the actual observations, not the residuals. I apologize for that typo. But we would expect that thing. We expect the autocorrelation function to basically just kind of be like just have bars of like roughly height 0, right? So kind of almost like having no bars at all. We would expect those autocorrelations to be 0, if in fact the observations are independent of one another. I mentioned this. Intuitively, we expect to see a deteriorating dependence among I don't know why I keep using that word residuals. Should be say amongst observations. This means that we expect to see a deteriorating sample autocorrelation function of the observations. Silly me. Don't know why I had residuals on my mind. And I mentioned that before, we did see a deteriorating pattern, but again, for a stationary time series, we expect to see that thing deteriorate far faster than what we saw in that graph before. Now, another tool that's used a lot is referred to as the sample partial autocorrelation function. You may or may not remember in 512, we did talk briefly about the idea of partial autocorrelation, right? It was the correlation equivalent to the partial f-test, which probably you remember maybe a little bit more vividly. Notation-wise, instead of r sub k, we call this r sub kk. And intuitively, it's the sample autocorrelation of observations separated by k time points with the effects of intervening observations eliminated, right? That was what partial autocorrelation was in 512, right? Partial autocorrelation was something like the correlation between a bear's weight and their length after controlling for, right, their neck girth, for example. And that's what we're doing here. We're just controlling for these intermediary time points. This is the same plot as before, just now I want to call your attention to, right, the leftmost plot is the autocorrelation plot. If you look at the middle one is called the partial autocorrelation plot, so we can see what those are, right? That has, right, again, it's always going to be 1 for that lag 0. And then we see it's very close to 1 for lag 1. Then it drops quite a bit for lag 2, and it's actually negative, so we have a negative autocorrelation, partial autocorrelation at lag 2. And then it looks like it's kind of more or less zero, doesn't it? Looks like it flatlines for pretty much the rest of the way. Nothing crosses that red line, so nothing's really significantly different than zero. So those are all we would think of as more or less zero. And the rightmost plot, I mean, I guess while we have it up on our screen, that inverse autocorrelation plot, it is used here and there, but not nearly as widely used as these first two. We're going to focus entirely on the autocorrelation and partial autocorrelation plots. So, what do we do with these things? Why do I care about them? Well, we're looking for patterns. And there's a lot of different patterns that we might observe, and all these different patterns tell us different things. But the two main patterns we're looking for are these. And I'll tell you right now, it's not always obvious. In fact, it's often not obvious which of these two we're looking at. But we always try to break any autocorrelation and any partial autocorrelation plot into one of these two things, either dying down or cutting off. Right? So I actually have two examples right here in one slide. So, right, I mean, the autocorrelation plot is a very clear dying down pattern, right? It's a gradual reduction. It's never exactly zero, just getting closer and closer and closer to zero. So that autocorrelation plot is kind of like the perfect example of a dying down pattern. And the partial autocorrelation plot is a really good example of a cutting off, right? That is, it looks like it's something other than zero at lag 1, looks like it's probably something other than zero at lag 2, and then it seems like it immediately cuts off to zero. Agreed? That is, it drops, it cuts off, right, from lag 2 to lag 3. So the idea of like dying down and cutting off is almost kind of like, it's like conceptually, graphically, like a hill versus a cliff, right? The dying down is it looks kind of like a hill, right? The cutting off is it looks kind of like a cliff. Yeah, so I mentioned this actually. So one way to test for stationarity is to look at the SAC. The faster the SAC dies down or cuts off, the stronger the evidence of stationarity. Right, I also talked about, I guess there's a few things kind of embedded in this PowerPoint. We could always do significance tests. I talked about those red lines indicating, right, whether or not something's significant. And then also, right, anytime you're looking at these SACs or SPACs, right, those things go to like lag 20 or something, don't they? And so remember what it means for alpha to be 0.05, right? When you're looking at that red line and you're thinking of it as doing a significance test, right? An alpha of 0.05 is saying 5% of the time we falsely reject the null hypothesis. 5% of the time is 1 out of 20, right? So if I'm looking at like 20 different tests, if I'm looking at 20 different lags, I would, and none of them are significant, I would still expect to, right, have this kind of this red herring, right? This false positive. And you'll see that a lot, right? You'll see like a bunch of bars that are about 0 and then some like weird spike at lag 13. And it's tempting to say like, oh, that's interesting. Like what's going on at lag 13? But probably realistically what's going on is, well, I'm doing 20 tests. 1 out of 20 of them is going to be falsely significant. So that 13, like, there's no real reason to expect anything there. It's probably just a false positive. Now, how do we use the SAC and the SPAC? How do we use the SAC and SPAC to test which model is appropriate to use for a given time series? Well, we can show theoretically It's actually not too hard. I think I do prove this in my time series class. Um, that the true autocorrelation function will be 0, exactly 0, for all lags greater than q. That is, it's non-zero, it's non-zero, it's non-zero, and then all of a sudden it's 0, right? And so we would expect the sample autocorrelation, which approximates that true autocorrelation, to look greater than 0, greater than 0, greater than 0, and then cut off, be something very close to 0 after lag q. You could also prove that the true partial autocorrelation actually just converges to 0, but never quite gets there, so, right, dies down. So a moving average model of order q will have a sac that cuts off and a SPAC that dies down. We will see the autoregressive is the exact opposite of that. Right? An autoregressive model of order p cuts off after lag p, the SPAC cuts off after lag p, and the SAC dies down. Now, what about mixed models? There does exist, right? It's possible to model a combination of autoregressive and moving average. And again, it's possible to have real life phenomenon that are, right, better modeled by a combination than just kind of a pure version of one or the other. For a mixed model, we expect to see a dying down pattern of both SPAC and SAC. Now, realistically, it's rare to see complicated mixed models. So if you do think you have a mixed model, the general recommendation is you keep it simple and just do an order 1 for both of those things, and mix an autoregressive of order 1 with a moving average of order 1. And then this is just what a mixed model looks like. So probably what you would expect, right? So here I moved from Z instead of Y, right? The Z notation is kind of is saying that, hey, right, this may not be the original observation. I may have had to transform it to get something stationary, but I'm now working with something stationary. And so you can see I have that autoregressive part where Z sub t depends on Z sub t minus 1 and so forth. I also have, right, the A sub t minus 1 and A sub t minus 2. So I mean, that's probably how you would imagine you might combine it. Now, what if I look at my SAC and my SPAC and it looks like they're both cutting off? And sadly, I will tell you, in most real life situations, to be honest, even a lot of fake data sets, you look at the SAC and the SPAC and it looks like they're both cutting off. It turns out that there are no theoretical models in which that happens. So even though your sample version may look like that, it's just like a little bit of noise. And maybe just one's dying down very fast. But the reality is you can't have a model in which SAC and SPAC both cut off. So if it looks like that's what's happening, then that just means one is dying down quickly. And so what you basically do is you say, okay, of the two, which one seems like it's cutting off the most? Which one is cutting off the most abruptly? I'm going to say that's the one that's cutting off, and then by default, the other one is dying down. Now again, right, always a caveat. Anytime we do transformations, and we will very often do transformations when we're doing ARIMA modeling, again, it's very rare that your original data set, the original thing that you're modeling, is stationary. It's almost impossible. So almost always you have to do some type of transforming to get stationarity, which means that you want to reverse those transformations before you do any forecasting. All right. That's it for the mathematics. Let's wind down with the important diagnostic tool, and then we'll look at where to access this tool in terms of an example. So we're going to talk about something. They're equivalent. You get the Box-Peer statistics. I'm not sure how to pronounce that person's name. I don't want to butcher it and insult them, so I just call it the L-box statistic. Right, Q for the first one, Q star. They're both essentially similar, both intended to do the same thing. The L-box statistic tends to work better, so I'm going to focus on that one. Right, the Q star, the L-box statistic. So what is this thing? The L-box statistic, or the L-box diagnostic, looks at the correlation of the model residuals. So we're looking at the A sub t's from our time series model. Now, if the model is properly modeling the dependency between the observations, then the residuals of our time series model should be independent, right? So kind of the big picture idea is, right, I have dependency in my data. I want that dependency to be soaked up by the model, to be absorbed in its entirety by the model, and have no dependency left over. That idea of leftover dependency is in my model residuals, my A sub t's. And so I could test whether or not my time series model has adequately addressed the dependency by looking at whether or not there's dependency in my A sub t's. Now, the L-box statistics tends to look at residuals. Like it's like an aggregate function of residuals up to some value k. Typically, we look at like increments of 6. So like 6, 12, 18, 24. Right? Very, very broadly, this is the way I believe it's presented in our textbook. Right? The null hypothesis is our model's adequate. The alternative is the model's inadequate. Our textbook talks about comparing the Q star to a critical value, but doing it in SAS, it'll give us a p-value, right? Which is something that we're probably more comfortable or more used to using. Now, something to keep in mind, Q and Q star are very general statistics that could be used to measure how well any particular model is removing dependency for the data, right? So for example, we could use them on an exponential smoothing model to see whether there's any dependency in our exponential smoothing model. We could also use it on just like a 512 model, right? So it becomes a little bit like a generalized Durbin-Watson test. All right, so let's tie all this together. Let's go to our paper towel example. I think we looked at this example in our exponential smoothing lecture. It has 10 years worth of monthly paper towel sales. So we want to analyze those sales. What's the first step? Exactly, first step, plot the data, right? Look at a scatter plot. So there's our scatter plot, right? We got our paper towel sales. There's the great paper towel crash of 1995, right? Your parents may or may not be able to tell you about it, and you know they did have to live through it, unfortunately. So I look at this, and if I want to fit an ARIMA model, what's my next step? Well, yeah. If I want to do an ARIMA, what's my next step? Well, first off, I want it to look stationary, right? And it does not look stationary to me. There is not a common mean, right? That does not look like a horizontal line. So I can start off by looking at the difference of the data. All right, instead of the y sub t, I look at the z sub t, where z sub t is y sub t minus y sub t minus 1. The z sub t looks like this. That looks pretty good, right? It says simple difference. I just click that little triangle button, right? In the upper left, that triangle button means difference. Certainly looks like a horizontal line, right? The variance looks roughly even. Now remember, we're looking for like dramatic departures from a common variance, and right, it looks like there might be like a couple cases where it like zigs down a bit or zigs up, but for the most part, it looks relatively even. It's not glaringly. There's not like a glaring obvious violation of common variance, right? Anytime you find yourself kind of waffling back and forth, you're probably okay. So now I have my data set, right? Or I have my stationary scatter plot. What's the next step? The next step, you're absolutely right, is to look at the autocorrelation functions. Yeah, data appears stationary after a single differencing operator. Next step is to look at the autocorrelation function. Okay. So here's our autocorrelation functions. We have the SAC and the SPAC. It's tricky. They both, to be honest, they both look like they cut off, don't they? They both look like they cut off. The autocorrelation looks like it cuts off after 1. The partial autocorrelation looks like it cuts off after 2. But we know that's not possible. So we have to think about which one we think cuts down the most. I think the autocorrelation cuts down the most. So if we were to buy into that, that means we'd be fitting a moving average model of order 1. That said, if you disagreed with me and said, I don't know, I think the partial autocorrelation cuts off the most, or if you just wanted to say, I can't even tell, there's nothing wrong with also fitting. Well, if we decided it was the partial autocorrelation cutting off at 2, that would be what? That would be an autoregressive model of order 2. There's nothing wrong with fitting both of those models and comparing them, right? And maybe that's something that you could do on your own. But for the sake of this lecture, I'm going to stick with what I'm seeing, which is a farther drop off between 1 and 2. Like I'm looking at that sort of 1 to 2, and then onward it's like a dying down in the SPAC. And in the SAC, I'm seeing like there's like a pretty high bar at 1, and then boom, it just looks all close to 0 from then on out as a moving average model of order 1. Yeah, SAC seems to cut off more abruptly than the SPAC. I'll admit it's a tough one to see. I've been doing this a lot longer than you have. There's nothing wrong with fitting multiple models and comparing them. If we buy into the SAC cutting off at lag 1, that tells us a moving average model of order 1. All right, so there it is. My graph, right, says IMA, right, integrated moving average. That 1, 1 is basically saying that we integrated it once. Integration is just, right, how many differences you took. So it's saying I took 1 difference, just the first difference, and it's a moving average of order 1. And look at that. These models are pretty powerful, aren't they? Like, this data looks so crazy. Like, if you were to look at that data in 512, you'd be like, how the heck am I going to fit that? But these ARIMA models do a very good job of chasing the data, don't they? Those predictions actually look pretty good. Now here, so how do I get this thing right here? To get this thing right here, I have to click the if you look over on the right hand side, we got like our buttons there on our time series dashboard. If you click where it says P equals 0.05, you'll get something that looks like this. And this gives us the L box test. The L box test is what SAS is calling the white noise test. And if you were to mouse over, you can't do that because this is a PowerPoint. But if you actually had this dashboard on your computer and you moused over any of those bars, it would tell you exactly what the p-value of that bar is. Now, SAS has red lines, right? It has a red line we could see at 0.01. It has a red line at 0.05. So I could see that all these bars, right? In this case, the small bars are indicative of a large p-value. So all of these bars are well above 0.05, which is good, right? Because that means we failed to reject the null hypothesis, and our null hypothesis was our model was adequate. So this is basically indicating that our residuals are independent of one another. So this is a very, very, very good looking L-box test, or very good looking situation. Our dependency has been adequately modeled, has been sort of transferred into the time series equation successfully. Right, and then of course I can click on the beta hats to go ahead and get my model equation, right? So there's my model equation, right? I only have one coefficient, it's just order 1, so my coefficient's at negative 0.35. And then if I wanted some model fit diagnostics, I can click that sigma square button on my dashboard. And then that would give me something like this, right? Which I could then use these metrics to compare other models with one another, right? Would be maybe the primary use of some of these statistics of fit. I could compare mean squared error, root mean squared error. I could also, compare the IC and the BIC, that information criteria or Bayesian information criteria. All right, that wraps up our lecture.
All right, let's conclude with some closing comments. First off, a pretty common rule of thumb is that you should really have at least 50 observations to build a good ARIMA model. So anything less than that in ARIMA models maybe not the most optimal choice. The second comment, something I think I might have mentioned earlier, how well an ARIMA model works, how well it's going to succeed, is heavily dictated in terms of how well that stationarity is achieved. That stationarity in achieving it's a really big deal. And so what that implies, and it implies our third bullet point. The implication is that these ARIMA models are not always ideal for complicated trends, right? Complicated trends where we have it going up for a while, down for a while, it's linear for a bit, flat for a bit, maybe curved for a bit. These types of models, it's very difficult to actually get that stationarity. And so because of that, since that stationarity is so important, right, the ARIMA model is not an optimal choice. So in situations where we have these kind of dynamic, changing trends, ARIMA models don't always work so well. Instead, right, what we would do is we would fall back on an exponential smoothing model. Exponential smoothing models, we talked about are kind of optimized for that type of situation. All right, bye for now.